Let me once again welcome everyone. Thank you for joining today's presentation and today's webinar. Our webinar is organized by Nanomaterials, so the journal that belongs to MDPI. And the MDPI is a pioneer in scholarly open access publishing, and we support academic community since 1996. Our headquarters is based in Switzerland, and our mission is to foster open scientific exchange in all forms across all disciplines. Currently, we have more than 400 diverse open access journals, which include 413 peer-reviewed journals and 9 conference journals. And we are supported by more than 115,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. As I mentioned, this webinar is also organized by journal Nanomaterials, which is an international peer-reviewed journal published in open access format, semi-monthly by MDPI. The journal is focused on publishing research articles, communications review papers, and show notes that are relevant to any field that involves nanomaterials, nanoscale materials, with respect to the science and application. This is a short program of today's webinar. So the first part is my short introduction. I will also say a few words in the next slides how the webinar will work and how the attendees can ask questions, if of course there will be any, to our chair and speaker today. Then we will have the talk from Professor Albert Chin, and after that we will have a Q&A questions. But if you will have during the presentation of Professor Chin any questions, you can ask them in the Q&A box, and after the talk Professor will be reading the questions and reply to them. After that, we will just have a short thank you note for and closing the webinar. Regarding the special issues that are relevant for this webinar, there is a special issue that is guest edited by our associate editor of the section Nanoelectronics, Nanosensors and Devices. Our associate editor has a special issue, which you can see here on the slide. It's a review collection in nanoelectronics, nanosensors, and devices. This is the section that Professor Chin belongs to, but from what I heard, Professor will be also guest editing the special issue in nanomaterials. I hope that he will also say a few words about that during his talk. As I said, you can ask the questions using the Q&A box, which you can see on your screens as well. And now I will give the voice to our chair and the speaker, Professor Albert Chin from National Yang-Ming Chiao-Tung University in Taiwan. So please, here you go.
Okay, thank you for introduction. Actually, I am also the IEEE Distinguished Lecturer, so I give many talks in IEEE. Before we start the technical part, we also have a brief introduction of like IEEE Electron Device Society, just like nanomaterials. So it's exactly the same. Okay, the title of my talk is Breaking Moore's Law Barrier Transistors for Three-Dimensional Brain-Mimicking IC Architecture. So the content of this talk you can find from many of our publications in the IEEE journal, and also the special issue in the nanomaterial for electron device. I was the guest editor. You can find from the nanomaterials. Okay, here shows the outline. The first one is challenges and the opportunities. Next, three-dimensional integrated circuit, then high mobility MOS transistors on VLSI backend for the three-dimensional integrated circuit conclusions. Before we start the technical talk, let's introduce the fundamentals of a MOS transistor. This is a simple structure of MOS transistor. It has a three-terminal source, drain. The electron can flow from source to drain and controlled by gate. So the structure for the MOS transistor is a vertical capacitor here plus horizontal electrical field. So it will translate the gate voltage into the output current to drive the circuit as fast as we can. So we need a high output current. Okay, please notice that the source and the drain contact we must have has N plus. N plus means highly doped electrons on the P body silicon. So between N and the P, a carrier depletion region showing here. Carrier depletion region means that we do not have electron nor holes inside this region because the N plus region will provide the electron. P body will give you holes, and the electrons and the hole will annihilate, cancel each other to form a depletion region. Okay, and the depletion region can extend from source to drain if we increase the reverse bias voltage. So this is important transistor characteristics. This is output current as a function of drain voltage. The drain voltage here. Once the transistor turned on at a low voltage, this is a low voltage region. It behaves as a resistor because the IV curve is linear. So it's a linear, we also call it a linear region. However, the output current gradually saturates at a higher drain voltage. Why? Because the current is limited by the saturation velocity passing the electrons passing through the depletion region, or give you the same inversion charge. So it will saturate and fade out the output current. So that is a brief introduction. Okay, why do we want to scale down the device size? Because of cost. The cost reduction engine that drives the industry and enables energy efficiency. This is energy efficiency as the past years. More than 1 million times reduction in energy per transistor already happened in past 30 years. So if we scale down the transistor size, we can put more transistor in silicon chip, and at the same time, each transistor will have a lower power, 1 million time reduction. So that's an advantage. So we can right now put the many transistors in a single chip. However, as the device getting down to the nanometer regime, this is a long channel, this is a nanometer region. So you can see that the depletion region will close to each other, and the leakage current and create the leakage current. We call this effect, the increasing leakage current, called the short channel effect. The short channel effect will differently increase the gate current so we cannot form a large integrated circuit. So as we already talked in the previous slide, we need to put more transistors in a single chip for the artificial intelligence, for example. So we must solve the short chain effect, the lead current through the silicon body. The simplest way is to cut the silicon body using a very thin silicon layer to reduce the lead current. So last comes the idea of the FinFET. This is a structure of FinFET. And if we rotate 90 degrees of a FinFET, we will have a narrow sheet transistor showing here. The advantage for narrow sheet transistor, which will be the most perfect transistor up to now, up to the history of electron device, is that it can have even smaller area compared with the silicon FinFET. As you know, the 2 nanometer gate-all-around nanosheet integrator is planning to manufacture in this year in Taiwan. Yes. Here shows the downscaling roadmap, technology roadmap. This was proposed by the IMEC. The Moore's law of downscaling transistor size has slowed from every 2 years. In the past, every 2 years, we have a new technology, no. But right now, the downscaling time increased from 2 years into 3 years. Why? Because the technology downscaling becomes more difficult. However, starting from this year, the 2 nanometer node transistor to the end of roadmap, we are going to use the nanosheet transistor we already talk about in the previous slide. So we can only scale down the cell size and the N-FET and the P-FET distance. For example, we will have a complementary FET structure. So we stack the N-FET and the P-FET on the top to scale down the silicon transistor area. The last node will be the 2D material atomic layer thickness for A2 node. A2 means 2 angstrom. But however, no solution for 12-inch manufacture up to date. So maybe if we cannot solve the manufacture problem, the 2D material cannot be realized in any manufacturer, no. Starting from this year, for sub-1 nanometer node, for example, the A7 to A3 node, we need a hyper-NA EUV, a new EUV lithography machine. So in the past, the EUV has been used for 3 nodes from A7, A5, N3. And right now, we are going to use a high NA EUV starting from N2, A14, and A10. So each generation of the EUV lithography machine can only last for 3 years. However, the EUV equipment is very expensive. The EUV, the first gen EUV has a price 180 million of US dollar. The next generation EUV lithography system, we call the high NA EUV, is 360 million, double the price. So the hyper-NA EUV is projected to RCS 720 million per equipment. Unfortunately, the R&D cost of a hyper-NA EUV is too high and cannot be afforded by ASML, and probably only used for one company, which is TSMC. So it will be questionable if we can have a hyper-NA EUV for the after the 2031. And here shows the problem of a two-dimensional 2D material. For example, molybdenum disulfide. The single atomic layer molybdenum disulfide has a direct energy band gap of 1.8 eV, which is perfect for N-type transistor. N-type transistor means that this transistor will be driven by the electrons. However, the major challenge to form the defect-free monolayer material on 12-inch silicon wafer, we must, the equipment right now is the 12-inch wafer for manufacture. So we must use the same wafer size to manufacture the single layer two-dimensional material. Another issue is that no high hole mobility 2D material for P-type hole conductive PMOS. So that's a challenge. The challenge for materials like a 2D material is very difficult. In the past, the high mobility material like the 3,5 Indian gallium arsenide is needed for ultra low power integrated circuit. It operates at a low drain voltage. However, up to now, the Indian gallium arsenide made on silicon is still a challenging issue since the early study from the 1980s. This is due to the large lattice mismatch, high dislocation densities, stacking fault, and twin defect. Those defects will create a high of current. As we already said, the transient leakage current is very important because we are going to put trillions of transistors in a single chip. So if the transistor just leakage current just increase slightly, the whole trillions of transistors in a single chip will consume a high DC power, which is not tolerable at all. So the Indian gallium arsenide on silicon was dead. That's a material challenge. You may have heard from the news the future two-dimensional material for manufacture. The 2D material, however, has been studied for decades long time. But the effective mobility at 5E12 CN² VS for high-speed IC is still 3 times lower than 5 nanometer silicon. The silicon nanosheet FET used for the production this year. Besides the vertical thickness for nanosheet transistor is limited by the multiple high-K gate stacks plus the channel materials. So the 2D material can only partially scale down the vertical nanostack. You may think about, well, is the slightly smaller, the 3 times smaller mobility make huge difference or not? Unfortunately, the small mobility increase operation voltage and the switching power, which is opposite to the low power consumption criteria in the integrated circuit. You may say that how big is the power consumption in modern AI chip? Well, more than 1,000 watt, which is huge. So the increasing the power consumption is not allowed at all. Okay, so what will be next in the electron device? In the commercial market, we have 4 times 10 to the power of 12 FETs. In last year, this is a projection of the increase the transistor size expected by Intel. It said that at the year 2030, the transistor size will go to 1 trillion. Unfortunately, however, even at the last year, the transistor size already more than 4 trillion transistors, much earlier than the previous prediction. How about the memory? The high bandwidth memory HBM4 already this product already announced in you can buy this product this month, and the 2 times 10 to the power of 12 using the 118 layers cells flash memory was realized in commercial product last year versus 10 to the power of 11 neurons in our human brain. So the electron device used for the AI chip is already more than 1 order of magnitude higher than our neurons in the brain. So we need to ask a question, what are the next for electron device? This is the improvement of the CPU in the past. Over the past 24 years from 2001 to this year, the transistor size decreased 32 times from 130 nanometer to 4 nanometer node. However, the speed only increased from 1.5 gigahertz to the 4.3 gigahertz, about 3 times. Even soon reaching the EOV lithography and the quantum mechanical scaling limit. To improve the speed, the multi-core processor is used, but wasting more power because you have the power is consumed at each core. So how to solve the challenge? Yes, we can learn the solution from our brain, yes. But before we talk about our brain, let's see AI accelerator. The AI accelerator performance improving is quite fast compared with the microprocessor. The performance of AI engine has improved 1 million times in the past 10 years. 1 million times. The improvement is due to the parallel design from the CPU to GPU and or using the NPU structure. And that's a logic unit. How about memory? In the memory, they use the 3D package high bandwidth memory or the level 3 SRAM. But the most significant change is to form the high-speed interconnect between the logic unit and the memory. That's the breakthrough to decrease von Neumann's delay significantly. Here shows energy charging for the AI accelerator. OpenAI CEO Sam Altman, the Achilles heel of AI is its energy consumption. So he is still chasing billions of dollars to build a new AI chips. NVIDIA's CEO Jason Huang, we need 14 different plans shown here. 4 more suns to power the future AI GPU tech. So which is obviously impossible. So those challenges are the our duty of IEEE Electron Device Society. Our IEEE Electron Device Society is promoting excellence in the field of electron device for the benefit of humanity. Yes, for the whole human being. So we must solve the power consumption problem in the AI accelerator. I've been the technical committee chair on electronics material, also the committee chair on compound semiconductor device and the circuits. The circuit is very important if you want to understand the device. So let's compare the advanced AI accelerator with our brain. The power consumption is typical 1,000 watts, but our brain is only 20 watts. Yes. Orders of making it different. The strength is a much faster calculation, but our brain is smarter creativity and multifunctionality. There are many devices used for the AI accelerator, but we only have a neuron in our brain. The major difference is massive 3D parallel computing in our brain, in the hardware only. So huge challenge and opportunities. Yes, opportunities are in front of us to realize high performance and power saving ICs as we learn from our brain. So what's the limiting factor for AI accelerator? The performance limiting factor is not the front-end transistors. As we already said, the most advanced AI chip has 4 trillion transistors in a single chip. So it's not in the transistors. It's due to the interconnect. The size of thousands of miles long interconnect in a silicon chip is much larger than the transistors. This is a delay as a function of technology node. The major power consumption in advanced IC is from the interconnect, not the transistor. If we scale down the transistor size, the power consumption can be smaller and smaller. So to address the speed and the power challenge, we pioneered the first 3D IC as early as 2004 and present in IEDM in the following. Okay, here shows the difference between 2D and the 3-dimensional IC. The major advantage for the 3D case is a higher density, heterogeneous integration, and the most important thing is a much lower power consumption compared with 2D case. How much lower the power consumption? Yes, the consumed power in the integrated circuit versus frequency in interconnect can be obtained from the calibrate equivalent circuit model shown here. And electromagnetic calculation uses S parameters. This is a result. This is a power loss as a function of the frequency. As you can see now, the operational frequency can be largely increased. You can see the red arrow here. Using the 3D or 2 times 3D, the operation frequency can be increased a lot. And at the same frequency, the dynamic power can be largely decreased by the 3D integration. The problem showing again, I think it's due to a laser pointer because the laser point is not moving. So let me try to escape and try to start, but without the laser pointer. Okay, so there's no laser pointer. So right now, everything becomes fine. So actually, we made the first 3D IC as early as 2004 using the wafer bonding and the smart card technology. We made the single crystal germanium on amorphous silicon dioxide to form the 3D structure. The germanium transistors were fabricated on the VLSI backend, the silicon dioxide, or the silicon nitride with little effect on the bottom silicon CMOS because the temperature of germanium CMOS is significantly lower than the silicon. So this is a 3D transistor, germanium transistor. This is the Hall mobility as a function of a vertical electrical field. This transistor has 2.6 times higher Hall mobility than this curve. This curve is a silicon dioxide universal mobility. So we can reduce the operation of vertical effective field from 1 megawatt cm to half megawatt cm, which means that we can have 4 times the AC power reduction or operation power reduction. The germanium CMOS is also reasonable. So the higher mobility germanium is an ideal candidate for low voltage green transistor, shown here. Okay, you may ask, why do we need high mobility? Yes, lower the vertical field, the gate voltage, but the even important is that it can lower the drain voltage for the transistor. As we know, the transistor is operate at the saturation region, not a linear region shown here. The flat IDVD region. For low power operation, the VD should be as small as possible, but you cannot go into a linear region. The slope of the linear region shown here is proportional to the transistor's mobility. So what is an ideal transistor? The ideal transistor should be turned on very fast and become saturated. But in reality, there is no such ideal transistor. So we must have a linear region. The only thing we can improve the useless voltage drop in the linear region is try to use a high mobility material, because the mobility is proportional to the slope, the IDVD slope. So in the past, yes, the Intel start to use SRAM silicon for the IC product, and the AV company right now use the strain silicon material because it can operate at a lower power consumption region. So that's an idea. Our published germanium insulated paper has been cited by the International Technology Roadmap for Semiconductors in the emerging research device. This is the first time any invention from Taiwan has been listed in the ITR's roadmap, technology roadmap. So after 16 years of our paper published in IEDM, using a similar bonding technology, but we use the wafer bonding. But TSM use package technology. Apple is the first to bring the package 2.5D CPU for A10 microprocessor in iPhone 7. However, the major limitation of such package label 2.5D is the too few micro bump interconnect. That is far less than the brain structure, orders of magnitude smaller than our brain. So the present die stacking technology is 2.5D. It's not the 3D, we call the 2.5D, which is far from the high interconnect density in our brain. To solve this limit, we pioneered again the first monolithic 3D published in the IEDM 2015, which may provide more than 100,000 times higher interconnect density than the present packaged 2.5D, enabling the electronic neurons. Here shows the problem of the packaged 2.5D AI accelerator. As we know, the power consumption increased from the CPU, gaming CPU, to AI GPU. The huge power consumption up to 1,000 watts heat up the GPU chip. And the most problem is that the packaging materials. So the heating effect makes the whole chip bending, die shift, and the interconnect failures. That limiting the package 2.5D IC density. Actually, as you know, this is a real case happened last year. And it spent another 3 to 6 months to solve this issue. The solution is very simple. You need to decrease the GPU temperature by redesign the transistor density. But so that increase the cost of a silicon chip. The next topic will be high mobility transistor on VLSI backend for the 3D IC. So the real 3D IC, not the packaged 3D IC. This is our proposed 3D IC architecture, which mimic the 3D neurons in our brain, using the logic and the memory device made on the amorphous silicon dioxide. The blue color is amorphous silicon dioxide. Above the 2D silicon ICs, 2D silicon IC is made on single crystal silicon wafer. But our transistor must made on the amorphous silicon dioxide, so you cannot have a single crystal. Here shows the charge density distribution of the metal oxide. The high mobility is still visible in narrow crystal metal oxide, unlike the single crystal silicon. By new physical mechanism, the overlapped large radius NS orbitals and the small effective mass. From the first principle quantum mechanical calculation, the charge density distribution of zinc oxide shows close 4s orbitals to lead the high mobility. So that's a reason to give you high mobility, which even stronger in 5s tin dioxide. So we reported this result in IEDM 2015. The nanosheet SNO2 N-type made on amorphous silicon dioxide is an ideal candidate for monolithic 3D architecture to mimic the BioBrain. The 4.5 nanometer thickness is even smaller than the 7 nanometer nanosheet silicon. In 2 nanometer nanosheet FET used the production this year. So how about the mobility? For the first time, the metal oxynitride nanosheet NFET made on amorphous silicon dioxide reaches a high mobility 325 cm square vs mobility at 5E12. The red point here, even higher than single crystal NFET at the same 5 nanometer body thickness. Please notice that our data is also higher than the 2D materials by 3 to 4 times higher. How about the PFET? As we know, to lower the DC power consumption, high mobility metal oxide PFET is also required from the first principle quantum mechanical calculation. The tin monoxide is one of the best candidates for PFET due to the very small Hall effective mass without the heavy Hall band. In almost all the semiconductor, we have a light Hall band and a heavy Hall band. But in the tin monoxide, we have only one band. The passive and the UV anneal, the high-K tin monoxide nanosheet PFET made on amorphous silicon dioxide has a mobility as high as 20.7 at 5 times 10 to the power of 12 Hall density. The best data for metal oxide PFET reaching 20% of a single crystal silicon PMOS. We report this result in the Nanomaterials this year. Right now, we can even reach almost double the mobility, about the 50% of a single crystal silicon. Our paper published in the scientific report has become the top 100 scientific report physics paper in the past. Our paper published in Nanomaterials in this field has been a cover page of Nanomaterials. I also give a plenary talk in IEEE EDM technology toward the three-dimensional brain-mimicking IC architecture. The other plenary speakers are the VP from ASML and also the CTO and the senior VP from Global Foundry. And our result also are reported in a technical brief in the IEEE Electron Device Society newsletter. The title is Brain Electron Device Raising the Trend. Earth crisis. This is energy consumption as a function of years. The projection of world net electricity increased monotonically with time. The EOV in TSMC is over 10 billion kilowatt hours and will increase several times in high-NA EOV started to using this year. Stephen Hawking warned repeatedly that Earth could be doomed by human beings and get burned a year 2600 due to the huge increase of power consumption. So we must solve the power consumption using a new technology, especially the AI chip. Because the time limit, I only want to say that our pioneered monolith 3D integration has been listed in the future technology by International Electron Device Meeting, IEDM, which has a high chance to be implemented into future IC manufacture, like our previous pioneered high-K CMOS, high-K flash memory, and the 3D IC cases. Thank you for your attention. Questions?
Thank you very much. I think that there was one question added on the chat. But please, if anybody has any questions, please add them in the Q&A box or in the chat. It will be also fine. But the first question was why 2D consumes more power than 3D?
Which one consumes? Why the 3D has a lower power consumption, right?
Oh, this is the question to the attendee who asked the question.
Okay. Why? The answer is very simple. Let me find out the slide. Okay. This is a slide. The 3D layer, just like so we can reach the 3D by folding the 2D IC chip into the 3D. Certainly the interconnect length will be much reduced. So as we already said that all the power consumption is in the interconnect, it's not in the transistor at all. So once the interconnect, by folding from the 2D into the 3D case, certainly the 3D can reduce the power consumption huge. Okay.
Do we have any other questions, or maybe the person who asked the previous question has anything to add or ask additionally? In the chat, I also provided the information and the website of the special issue that is guest edited by Professor Chin and Professor Wu. So if you would like to check, please feel free. The same with the questions. I think that your presentation was too clear and we don't have any more questions. I think that we will be about to finish. If there is no more questions, let's wait a moment if somebody would like to type anything else.
I give a presentation in IEEE many times. So that's a reason I'm trying to show the whole idea and the future trend. Very clear and simple, easy to understand.
I believe that our attendees enjoyed your presentation and talk a lot. I was also listening during your presentation. So I think that everything was very clear. And maybe if these attendees will have any questions, they can contact you directly by email
Yes.
to discuss. So please feel free to contact our speaker. And so if we don't have any questions now, I would like to thank everybody for joining, and of course thank our chair and speaker at this webinar, and thank him for his support of nanomaterials. I also believe that there will be a lot of scholars interested in contributing to your newly opened special issue.
Thank you. Thank you. Bye-bye.
Thank you very much, everyone. Have a nice day.